My name is Curt Beckmann. I'm a principal architect at Brocade, and I'm chair of Forwarding Abstractions Working Group at the Open Networking Foundation. Colin was pretty active in that working group up until about a year ago, and then he kind of mysteriously went silent, and I didn't know why for a few weeks, and then I knew why.
I'm Colin. I'm at IBM in Austin, and also, I don't know, I guess natively resident to OpenDaylight.org or something at this point. So I'm just going to get started, and I'm going to try and give you an idea of what this talk is about. So the high-level point is OpenFlow 1.3 is coming, and it's coming on hardware, it's coming on software, but it might, first of all, it's not going to solve all problems, and it might not even solve the problems you wanted to solve and you think it might solve very well. But fortunately, Curt and I have been thinking about it for a while. Curt has been thinking for the last year in addition to that, and we have some ideas. So just as a high-level thing, OpenFlow 1.3 and now 1.4 are coming, and their good news is that they're fixing a couple of the problems that we had before. One of them, in addition to just the simple things like, hey, we can now route on MPLS and IPv6, which we've been able to do with extensions for a while now, but have formal support for that. They have multiple tables. And if anybody's actually tried to build a real controller on top of real hardware, they sort of understand that if you try and do more than one thing all in this single table that's in OpenFlow 1.0, that you end up with the number of rules growing exponentially as your concerns go up. And so there's some hope when we have multiple tables that we will separate our concerns into different tables. So you have one table about VLAN tagging and ACLs, and a different table about forwarding based on L2 destination MAC addresses, and a different table about doing like ECMP. Heaven forbid we be able to separate our concerns so well. The other good news is that hardware and software is coming along. The last ONF Plugfest actually had somewhat decent results in terms of OpenFlow 1.3 compatibility. And software support, in particular in Hydrogen, exists for OpenFlow 1.3. You can get things up and running and connect them, and they will actually work. That's about the total of the good news I have about OpenFlow 1.3. And the bad news, the good news about the bad news is that we have some ideas how to get around it. But the bad news is there's lots and lots of options in OpenFlow 1.3. Just to name a few, figuring out what table numbers are what kinds of tables, figuring out what the matches you can have in each table, what the actions in each table are, what config messages you're going to send, whether those config messages are sent over OFConfig, which as far as I can tell, nobody supports in hardware or even in software in most cases, or if they're sent directly into the control plane, and how those interact with each other if you're going to do both. Then once you have all these options, how do you discover them or negotiate them? Heaven forbid you try and tell hardware what to do. Right now, the things that use OpenFlow 1.3 typically are for soft switches, and they say, like, give me a table that matches on MPLS tags, input port, and VLAN. And if you tell that to a Broadcom ASIC, I can promise you that it's going to tell you to go screw yourself. That's not a table that exists in the hardware because it's not something that people really want to go do except for the one TCAM table that happens to do everything. And finally, and sort of this is the part everybody cares about, how do you map application and functionality onto these OpenFlow 1.3 primitives, and then from there onto hardware in a way that the hardware can actually support? And TTPs, which is sort of the side of it, really are about, we started off thinking about hardware. Soft switches, the problem is just easier because they can just reconfigure. They can implement the OpenFlow spec if they so choose. So just to drive this point home, I'm going to tell a few war stories from my own personal experience in the last 2 years of using OpenFlow. And unlike a lot of people, I've used OpenFlow on real hardware to try and do things with controllers. And I've sort of had both some exposure to the hardware side of things and the controller side of things, because at least until recently, IBM made networking hardware. The OpenFlow 1.0 implementation on our switches, in particular the IBM GA264, which is the one I've had the most experience with, it's our 10 gig top of rack switch, allows for you to program in OpenFlow 1.0 the L2 destination MAC address forwarding table, which is a pretty cool trick. But to get a rule in, you have to first wildcard every single field but the destination MAC address, VLAN ID, and VLAN priority code point. Then you have to specify all three of those fields exactly with an exact match, and then you have to set the OpenFlow priority to 1,000. If you do all of those things, magically it appears in the L2 table, which has about 100 and some thousand entries, as compared to about 1,000 entries in the TCAM. And so this is really cool, and we actually built features for that switch into controllers that we shipped. But of course, we had to have all these weird escape cases in our controllers that were like, if it's not an IBM switch, I don't know, throw your hands up in the air and do a dance. And so getting this to work across different hardware and trying to come up with standardized ways to do with this, that was actually why I started attending the Forward Abstractions Working Group with Curt and sort of got into all of this. It was to try and expose this richer hardware underneath up into applications and be able to use them. And so the second story I'll tell is about testing OpenFlow 1.3 support for OpenDaylight. And I have fewer of these actual scars on my body than other people, but I can point you at the people who have the scars. Abhijit right there is probably the person to go and find if you want to hear the exact war stories. But basically, I think we used 3 different soft switches to try and get the coverage for OpenFlow 1.3 plugin. And even across those 3 soft switches, we couldn't get full coverage. And there were times when the soft switches would crash, reject messages, or just not acknowledge messages that were, as far as we can tell, wire valid. So this is sort of the state of affairs in OpenFlow 1.3 and sort of this trying to expose hardware. And so that's just sort of, this is a real problem. It's not one that I made up. And Curt has done a huge amount of hard work playing around with this. And I'm going to let him talk a little bit about sort of pipeline mapping and leading you into TTPs, which is sort of our approach to try and attack this.
Thanks, Colin. And I would say it's the work group has done a bunch of work, and I'll take the credit. So essentially, we've talked a little bit already about the limits of OpenFlow 1.3. I mean, the limits are, well, they give you a bunch of cool features, the MPLS and V6 and other things, and lots of tables to take care of the combinatorial problem. But that's their limits, right? So what comes with these multiple tables is a pipeline. Now, this multiple tables essentially translate into a pipeline. Boy, I'm going to have to put my glasses out. I either have to look at that one. Maybe I'll look at that one. As we said, many of the new features are optional, and how do we code for variable hardware? Because that's the reality, right? We have variable hardware out there. And it's not, though, it's not that we're trying to get the hardware to do something that it can't do. Very often, we know the hardware can do what we want it to do, and the question is, how do we manipulate that, you know, when we've got multiple tables and the tables are different? What we really want to do, of course, is hide the hardware under an abstraction layer. People don't want to code directly to hardware. It's not really best to expose flow entries up to all the applications. And across diverse hardware, there's going to be different flow entries in different tables. So how are we going to deal with that in the abstraction layer? That's the point of this talk. And we're glad you asked, but you know, hold that thought. So yeah, multiple tables is a pipeline. You know, there's a pipeline. That's kind of a dynamic pipeline. OpenFlow 1.3 is actually a control protocol, though. It's not a pipeline definition language or a pipeline constraint language. And that's kind of the challenge. OpenFlow 1.3 works by controlling an assumed pipeline, an implicit pipeline, essentially the full-blown OpenFlow abstract pipeline. OpenFlow 1.0 kind of did the same thing, but its assumed pipeline was a very simple pipeline, a single table, or at least Ben Pfaff likes to tell me that no, there's OpenFlow 1.0 allowed for multiple tables, but the controller didn't know about them, and so it would treat it like a single table. So what we need to do in 1.3, we want to take advantage of these multiple tables for the combinatorial problem that Colin's already mentioned. But this pipeline, that full vast 1.3 pipeline exceeds everything that any ASIC can do today, at least, and for quite some time. And so there's no way to map in advance all the possible pipelines to your device pipeline. I mean, for one thing, there's many ways to express what your chip can do, and you don't necessarily know how the controller is going to try and express a particular kind of functionality. And this is really challenging. Now, one good thing is that we don't really need to do this. We don't really need to pre-map everything. Real-world use cases seek to use some subset of that vast OpenFlow pipeline, this sort of sub-pipeline within the vast OpenFlow pipeline. So we could use a constrained version of that pipeline. But 1.3, OpenFlow 1.3 didn't create a pipeline constraint language. And so that's basically what we set out to do. I've jumped ahead of myself. We could retreat. There's 2 things we could do. We could go back to the single table. We've already talked about why that's not attractive, because even though some applications could maybe live with that, it doesn't really scale across broad applications. So what we need is multiple tables, and we need to have a way to scale that onto, or to map that onto ASICs. Adapting on the fly. Well, this is what happens when you adapt on the fly, adapt a pipeline on the fly. In here, on the fly, what I mean by that is while we're sending OpenFlow flow mod messages, that's not a good time to be changing the pipeline. And it turns out OpenFlow, as I said, flow mod messages are not a good pipeline constraint language. You have to get basically all the messages that you may ever get in order to really know for sure what the pipeline is. If you say, well, I'll sort of construct my pipeline after the first 100 flow mod messages, you're likely to get it wrong. The 101st or the 1001st or the 10,000th message will do a go-to to some table that you didn't know existed, and your assumptions about the pipeline are all wrong. So there's just too much dynamicism in the on-the-fly pipeline mapping thing, and it's too non-deterministic. And as it happens, operators don't like that. That might be okay in your lab. Oh, didn't work. I'll try it again. I'll back up. I'll retry. But operators want something that's proven, baked, known, et cetera. The real demand in the operator space is for, I want to be able to control on the fly. So I do like the idea of SDN. I want to be able to separate my control and data and manipulate that. But I'd like to have the pipeline stable and well-defined, at least well enough defined that I was able to try it out in my lab and know that the thing I'm running in my operational network, my production network, is the same, really, as the thing I tried in the lab. Now, there is no single pre-baked pipeline that's going to cover all the features and functionalities that we want. There's nothing looming about to burst onto the scene. We could say, well, we'll just wait for those silicon vendors to give us the answer. There will be new chips coming, and they'll add a lot of capability, but there'll be constant innovation in that space. They won't all be the same. They'll innovate in different directions. So it's not that we won't see a single pre-baked pipeline that gives us everything we want. But what if we had a framework that allowed us to have more than one pre-baked pipeline? That's what we're looking for. So that's what TTPs are about. First, let's touch a little bit on some of the pipeline mapping problems. There are many platforms with different pipelines that are out there and deployed. And there's some good news. The fully standardized functionality is commonly available in a bunch of ASICs and pipelines out there. But what's interesting is that a lot of these standards, fully standardized bits of functionality, can be combined in different ways. And so you combine layer 2 and layer 3, and there's many ways you can do that. There's variations in layer 3 space and variations in layer 2 space, and that adds to even more diversity. And then there's non-standard features like ACLs and PBR that are sort of pseudo-standard, not quite standard, and those add even more variability. So if you look at different things, some devices have one or a small number of router macs. Some of them are one per port. Some of them you can have many per port. Some of them the router macs are independent. Some of them it's masked and they're all within the same MAC range. And so there's quite a bit of variability in specific implementations. And you could say, well, the router didn't care the router spec, they didn't care about the MAC address. And the layer 2 guys, they didn't care about router MAC addresses. And so it ends up being an implementation detail. It's an important implementation detail when you're trying to control all of this from your SDN controller. And there's more, but I won't read it all to you. What are some of the pipeline mapping solutions? Well, a lot of people like the idea, well, let's just give me those really low level primitives, and I'll construct all the functionality they want using these primitives. And what's interesting about that, it sounds like a really good idea, but it's got its own pitfalls. ASICs often have those primitives, but often not in independent ways. So routing is made up of simpler primitives like rewrite source MAC, rewrite dest MAC, decrement TTL. And it turns out chips do that, but they only do them in conjunction with each other. And OpenFlow defines them separately. And so when you ask me for my capabilities, do I say yes or no when you ask me if I can do a source MAC rewrite? Well, I sort of can, but I sort of can't. Well, can you route? Yeah, but that's not the language that we're using. Adding richer capability exchange, seems like it would help, but because of the interplay between different functionalities, it would be essentially to do that right. You do TTPs, and you really need to know it in advance. As I mentioned already, future chips don't necessarily fix this. at least not for quite a long time. We often talk about x86, so, oh, we want to have an instruction set like we have for the x86, right? It was a common instruction set across all the x86s. Well, no, that's why there's an X in x86. They weren't all the same. There are differences there, particularly in some important ways, like the way the memory map worked and so on, the memory architecture. So, and that's part of the reason, right? And then as well as operating system, there's a reason why we don't code applications in x86 code. I mean, a few people do, but you kind of have to rebuild it. Mostly, we code in a little bit level, a little bit of an abstraction level, and we rebuild it for different platforms. So the key thing that we need to do is to get out of the runtime. Let's not sort out the pipeline while we're sending the OpenFlow flow mod messages, and that's what we propose. And this is how TTPs can help. Now, TTP stands for Table Type Patterns. It's a phrase that came from the Forwarding Abstractions Charter a long time ago, before we'd given a lot of thought to this. And so we've kept the name to refer to the first generation of these kind of pre-baked pipelines. And the larger category of sort of southbound agreed interfaces is negotiable data path models. So that's another larger bucket that we regard TTPs as being the first example of those. And one thing that we sometimes talk about is that, well, maybe TTPs are specific to OpenFlow 1.x, at least for the moment. Who knows? Maybe we don't know what OpenFlow 2.0 is. Maybe they'll still be covered by TTPs, or maybe there'll be some new category. But NDMs, they may extend beyond OpenFlow as well. So I'm certainly willing to have that conversation that NDMs might refer to some agreed interface for I2RS or PCEP or some other southbound interface from a controller perspective. So as I say, TTPs are the pre-baked pipelines, and they have specific switch functionality defined in OpenFlow 1.x terms. And with these TTPs, these well-defined sets of switch functionality, well-defined pipelines that are controllable because we know the table numbers and we know the matches and the actions that are associated with those TTPs, we can map those before runtime. We, the switch implementer. And as it happens, also controllers can code to them because all the mysteries that Colin was talking about. Okay, well, I sort of know about one category, one product line of one vendor's switches, but I don't know about another product line or another vendor. When you have TTPs, that's like an agreed level of functionality, and I can code to that TTP. It's like, okay, I can write my application to that TTP, and possibly to 2 or 3 TTPs. Each of those TTPs gives me enough to work with, and in that way, I may be able to cover dozens of pieces of equipment. So once a TTP is agreed, and that's part of the picture, and that I'll talk a little bit more about, that the switch and the controller have agreement on what a TTP is. Well, okay, what's the pipeline that we're using? What's the switch model that we're using? Those are just other ways to say the same thing. And once they have agreement, now there's not that non-determinism that we were faced with before. And so in that picture, the switch will support all of the messages that were described in the TTP, and the controller promises to only use the switches only use the messages that were described in the TTP. Okay, so as I mentioned, a TTP is a sort of a switch model, or it's a pipeline with specific instructions. That's what I keep referring to it as. And here are some examples that we've got listed here. You could come up with your own examples. So for example, a VLAN ID mapper mapping L2 switch, or a VXLAN gateway, NVGRE gateway, or potentially a VXLAN NVGRE bridge. A V4 router with ingress ACLs, or a V6 router with egress ACLs, or some combination of those. Each of those could be different TTPs. And as you can see, you can define TTPs that have a fairly rich amount of functionality, but are also constrained. I mean, the MPLS edge and core router doesn't necessarily do vid mapping, right? So you can see that you can bound it and potentially give yourself enough, or use someone else's and have enough to solve problems with. Another interesting thing about this is that TTPs help to sort out interoperability. So one of the problems now is if you go look in the marketplace, you can see that there's a controller out there and there's a switch out there. and maybe an application. What are the odds that you could put any two of them together and it would do what it was supposed to do? It's a kind of a crapshoot, and it's a modest crapshoot in 1.0, OF 1.0. There's not as many variables. In OF 1.3, the number of variables goes way up, and the odds of interoperability go way down. When you introduce TTPs, now people have ways of sort of, speaking the same language. Well, here's an application running on, say, OpenDaylight, and it supports this TTP vid mapper. And then here's a couple of switches that both claim to support vidmapper. And so I think there's a pretty good chance when I plug those together that they'll do what they're supposed to do. And that's what TTPs are about.
The only point I wanted to add on that slide is there's a critical thing at the end of the line in the dead center, which is that all messages after you've negotiated TTP are actually valid OF 1.3 or 1.4 messages. It's a strict subset. It's basically a negotiation that happens either out of band or in band. I think we have both ways of doing it. And then after that, it defines a subset of all possible OpenFlow messages which are legal under that negotiation. And so this is not inventing new OpenFlow functionality. It's not asking you to support new features. It's just saying, hey, let's at least agree on a sane subset of the whole spec so that way we can have a conversation that makes sense.
That's a very good point. And what's interesting is that agreement can include switch functionality or OpenFlow functionality that is listed as optional. And it can also leave out OpenFlow functionality that is currently identified as required. Essentially, it's a new agreement. And as such, it can be the agreement that you need it to be and doesn't have to include more than, it doesn't have to overly burden the device.
That was it.
All right.
Is it one TTP per physical or
No, it's very good question. So in OpenFlow, there's this notion of an OpenFlow capable switch that can support more than one, in theory, architecturally, more than one logical switch per physical switch. The idea is that it's a single TTP per logical switch. And most physical switches, I think today, not counting the soft switches, most physical switches are still currently one OpenFlow switch, logical switch, although sometimes they have non-OpenFlow pieces as well.
That's actually, well, IBM's has 4. Or you can configure up to 4 logical switches on our physical switches. So at least there's one counterexample to that.
I stand corrected. I've said that so many times. And Abhijit, you probably heard me say it, could have corrected me. Oops, I went past my slide. So this is just meant to walk through. You've kind of got all the data, but what is it all? How do you make sense of it? This is a little bit of an old slide. It's been around for about a year, but it's still fairly accurate. So essentially, for a variety of reasons, someone decides to create a new TTP, which you might say a new switch model to address a particular use case or category of use cases. It could be someone on the application or controller side said, boy, I could really architect a great SDN solution if I could just count on switches to do something. And I believe that there are switches out there that can, and I could do it using tables in this way. Or it could come from the switch side that they say, well, geez, we have 3 tables. Well, we've got 26 tables, but we really have 3 tables that kind of matter. So let me just expose these 3 tables. And this is how they work, and I'll just expose them upward. And then potentially, somebody else with a different switch says, well, those aren't exactly my tables, but I know I could map that. And so it could work from the switch up or from the app down, or it could work with a working group like mine, where we say we think there's some interesting functionality that we could describe this way. It's not particularly tied to a switch. Arguably, it's not even tied to a use case. But since the other side, the switch vendors are sort of not familiar necessarily with TTPs, and the app vendors are like thinking it's a trade secret or something. They don't want to describe these things. So basically, we're getting the ball rolling by introducing some TTPs. And we probably will also be willing to help folks that want to come to us and say, I've got a TTP in mind. Can you help me write it down? So you get busy and you write it down. You figure out what are the tables and what are the matches that happen in each table. What are the sequences? When do you send it to the controller? And when do you go to the next table and do some more matching? And you write all that down. You assign an identifier to it. It's a simple algorithm to pick the identifier. I mean, naming authority and some string and versions and so on. and then you share it. And I mean, without sharing, you don't really need a TTP. If you're going to do this all yourself, you could do a proprietary thing. Now, we do recognize NDAs may be relevant, that in early days, you may want to work with a partner and keep things quiet until you got stuff working. And we recognize that from a market perspective, nobody's going to have an incentive to do TTPs if they're going to give everything away right off the bat. So this way, they get at least some first mover advantage. It justifies that they invest, but then they get to join the SDN party, which is largely an open thing. SDN, the sensibilities are all about open. So really, NDA is meant to be kind of a temporary approach until you're ready to go public with it. Support is added to both sides. So the app and controller side need to support the TTP. The switch needs to support the TTP, but those don't have to be done necessarily exactly parallel. They can be done out of phase. You could discover that there's some great application out there and you want your switch to support it, and so you could add that support later. In any case, then you go to market with it, and the buyer is able to look and see at data sheets and find out what products, oh, this is an interesting application. That application is the kind of app I was looking for. It uses this TTP. Let me go see what switches support that TTP. Or conversely, I've got these TTPs already, or these switches in my network. I've already bought and deployed, and they're running some application, and they support certain TTPs. What other apps could I get that would work on these TTPs, or potentially other TTPs that my switches support? So the interoperability challenge is much more compressed. You have a lot more knowledge than you did before in terms of interoperability. So at some point, people buy pieces on both sides, they plug them together and they turn them on, and the devices chat with each other, and they figure out which is the device that they want. And there may be configurations on both sides that you can nudge it one way or the other depending on the nature of your environment or use case. And then after they've negotiated and agreed on the TTP, then it's normal OpenFlow. Like we said, they pass normal OpenFlow messages. There is, I should say, we mentioned 1.3, 1.4. The notion of TTPs is to support across a variety of different OpenFlow versions. So that's part of one of the lines in the TTP is which version of OpenFlow are we talking about. And it should be possible to carry them forward. So a 1.3 can also be a 1.4. And then once adoption occurs and some of the TTPs emerge as being more popular than others, it will obviously make sense to get third-party testing going on. We plan to make some tools, Python-based tools, whatever, that can take a TTP and generate some test stimulus so that even single parties can test their own devices and have some confidence that they'll interoperate. But what you really want is third-party testing, and so we expect that that'll happen. The test working group inside the ONF is eager to push this forward. So they're sort of an early adopter, you might say, and in fact are going to use TTPs as a language for defining test cases even before the applications or before the devices are TTP aware.
So it's probably useful if you go back one slide. So TTPs and their actual, concretely, if you're familiar with the OpenFlow spec, there's a table features message in OpenFlow 1.3, and I think it's earlier than that, but it's certainly in OpenFlow 1.3. It's like 3.5 or something. Anyway, there was a time when I used to know the exact spot. And basically, it just describes what a single table is supposed to be capable of. It was written mostly as a way to specify those tables to soft switches, as far as I can tell, which confuses me, but I wasn't in the room when it was created. But it basically describes what a table is capable of doing. And TTPs are really just a JSON representation of those data structures chained together into a pipeline, saying what transitions between tables are possible. So if you're looking for a concrete thing to think of as what a TTP is, it is a JSON file describing a series of tables using OpenFlow language and what transitions between tables are legal.
That's a good point, and let me just add to that, and then I'll take your question. And the picture that Colin just described about doing that with table features, of course, that happens really at connect time. And our picture is, as we sort of described here over in step 5, add support for the TTP. That doesn't happen at connect time, at least not in the early days. Down the road, there may be compilers that will allow you to take that JSON message and map that to your underlying hardware really dynamically, but still at connect time, not exactly at runtime, but just prior, minutes or seconds prior to runtime. So there is, conceptually, it's that same idea as a table features message, but well in advance instead of seconds in advance. So, and what was your question?
My question was, does the TTP help me to get the performance impact when I change the way I program it before I get to actual verification testing? And it help me estimate how much performance impact will I have in a pipeline?
I mean, an implementer could do that because they're the ones that know how they're going to map a TTP to the hardware. TTPs are meant to be implementation, largely implementation independent. They obviously can't be completely implementation independent. They can't, the underlying features need to be there. But the performance will often depend, as you say, on how that's mapped. It should be that two sort of equivalent TTPs can map with equal efficiency to the same underlying pipeline. But maybe not. Maybe one of them requires a lot more messaging, for example.
So is the question basically like, some switches implement OpenFlow by doing some of it in software and some of it in hardware, and the stuff that's done in software is incredibly slow, and so will this let you know that before in advance? Was that sort of your question? Or? Gotcha.
We don't create pipelines exactly. We describe pipelines. The pipeline's already there. So, I mean, I guess in the future, in some future hardware, you might be creating a pipeline more dynamically.
So in general, we've thought about TTPs so far. Maybe we should have this discussion after this talk, but about just exposing functionality that we couldn't get at before. So it's really about like a switch does a lot of things that OpenFlow 1.0 doesn't let me reasonably express. And this was sort of an attempt to try and figure out how far could we push OpenFlow 1.3 in making it possible for me to express concretely what it is a switch can and can't do. And so it's really about exposing new features and less about performance. And maybe we should talk offline about the performance impact, because that's not something I'm really familiar with. And it's not something I think I've discussed with Curt or heard discussed there.
No, there have been discussions about performance. And essentially, the idea that a TTP is expressing, these are the requirements that, from an application perspective, I need this from my switch. And some people say, well, the application will probably have performance requirements, things that it needs from the switch in performance terms as well. I think that is legitimate, but what I was also given some sage advice that said, if you start wrestling with performance, you'll never finish. And so we decided to sort of defer the performance question, but I do think it's legitimate. What I imagine is that once we have more third-party testing, we'll be able to sort of do performance tests, and somebody would know, okay, using this TTP, these are some performance metrics, but that would be sort of out of band. It would not be an in-band thing that the controller, at least not initially. Over time, maybe you could say, well, I'm going to go check the TTP performance website and figure out what performance I get for that TTP, but that would be down the road. Now I think
So I'm going to take over for a little bit, just because I'm a little bit more familiar with OpenDaylight's internals than Curt.
Seems like
so the question is sort of, you've heard about all of this stuff, but this could have been a talk that I gave at the ONF or the ONS or anywhere else, but it's at the OpenDaylight Summit. So what are the implications for OpenDaylight? There's a few things that are sort of interesting. The first thing is when we started doing TTPs way back when, it was really thinking about controllers as monolithic objects that were in and of themselves the consumer of the switch's functionality. And we're vaguely aware that apps were a thing that might be up there, but it wasn't really the forefront of our mind. And so we built it for controllers. But OpenDaylight in and of itself, while it's a controller, it's also platform-ish, and I would actually say just a platform. But so it's really hosting a set of apps that in and of themselves want the ability in order to do things with the switches. And so it's really negotiating with switches to try and get the functionality it needs on behalf of applications. And sort of exporting this and exposing this to applications isn't as perfectly obvious as you might hope. And so just to walk through one example, this is sort of where we get more speculative, and this is not stuff that's been built. This is stuff which Curt and I have talked about, and sort of we would really like to push forward in OpenDaylight. But so the idea is to put services in between applications and TTPs. So applications ask for services. That's already what happens in OpenDaylight. We have OSGI dependencies, and then those services in and of themselves presumably are closer to the hardware and might actually know what TTPs, what subsets of OpenFlow they need in order to provide their functionality, and they can express express that to OpenDaylight, which can then try to optimize essentially across the set of applications and services requirements that it has, try and find the best fit to the hardware that it has in its network, and then let the applications know as a consequence what services are available or not available in the network at a given point in time. And so really the key point is sort of deliver the requested services to applications on the hardware that we have. And this is just an optimization problem trying to satisfy things as best we can. And so with an example of sort of a create tunnels interface, you can imagine NVGRE and VXLAN and MPLS and STT and whatever other tunneling technology you can want, sort of being all of the set of ways that the tunnel service would be at the bottom end of it. And as long as it gets 2 matching endpoints in the places it needs, it can offer this service up to applications. And it just is going to tell the controller, these are the kinds of things I'm interested in. Tell me if they're around and try to get them for me. And so I'll let Curt take you through this, but this is sort of a really high-level view, and I'll walk you through sort of a more concrete in terms of actual sort of modules inside OpenDaylight that you might go touch in order to try and make this real. And we can follow up afterwards and offline, and we try and make this actually a real project inside OpenDaylight.
I think we may want to look into things like having the TTP also expressed in a YANG model, which MD SAL might be able to consume as is.
Yeah, no, I think that there. So the question was basically inside OpenDaylight right now, we are the OpenFlow 1.3 support is based around modeling the protocol as a YANG messages as YANG objects. And if you don't know what YANG is, it's anyway. I think it's mostly a JSON-like thing. And so the good news is that this is JSON-like, and probably there is a reasonable translation between TTPs and the current YANG model inside of OpenFlow 1.3. There's also been talks about the OpenFlow 1.3 model trying to just steal it from the ONF if the ONF is willing to publish a YANG model of OpenFlow 1.3. And I don't know if that's going to happen or not. But yeah, that's a really good point.
That is a good point. And I would say within our working group, we're not particularly hardwired to JSON. As it is, as you know, within working groups, you take the talent that's willing to step up. And so there was discussions about XML and YANG and JSON. And the people willing to step up were saying, well, I'm comfortable doing it in JSON. And I said, OK, we'll go with JSON until further notice, understanding that the translations are there and out there. And we believe, actually, that TTPs as a higher level construct can be represented a bunch of different ways, including JSON, XML, and probably YANG, although we haven't had someone that's enough of a YANG expert to know what we were doing in TTPs to actually say yes to that one. But I suspect.
Are you now a YANG expert, Abhijit? Can we rely on you?
Yeah, yeah, come to the calls more often. And he's like, oh, I'm going to duck that call. So this, yeah, I drew this picture. I thought it was interesting to draw the picture without knowing too much about OpenDaylight, in part to say, what would we like to have at a higher level? And since I conveniently don't know that much about OpenDaylight yet, I drew this picture, and then Colin's got some pictures that are more ODL aware. So in this picture, what we've got is a sort of a controller blob at the top, and we've got a set of hardware. And the way I've done this is like, OK, the guys with the square edges, they happen to be devices that will support create VXLAN tunnel. They may support other things as well, but in my picture here, they've got a TTP XYZ that supports VXLAN encapsulations. And they don't directly, because of the way OpenFlow works, there's no create VLAN tunnel message, but you can construct a create VLAN service on top of this VXLAN sort of TTP. Similarly, we got these round-cornered devices over here, and they're kind of similar to that, except they support a NVGRE tunneling capability, again using flow mod messages, but you can construct a create NVGRE tunnel service on top of that. And gosh, we're lucky. We've even got some bridges in there that can speak, that can convert between NVGRE and VXLAN. And there's a TTP available for those guys that has flow mods that allow you to build a service on top of that. Well, and then we've got some application. Maybe we have several applications, but at least we have one that wants a create tunnel API. And so either at build time or somehow dynamically, the application registers and says, gee, I'd like this API. Let me know when it's available. And then we've got an algorithm that's off to the side here. It's kind of aware about the devices that are out there. It's aware of applications and what APIs, what NBIs that they want. And it goes through an algorithm figuring out how it can bridge between, how it can deliver the requested northbound interface from the devices that are down there. And so, this supports a number of TTPs, but which of the TTPs, looking in my library, I've got a pool of plugins that map from TTPs to different NBIs. Which of those gives me the create tunnel NBI? And it goes through and it finds the ones that work. And so as I thought through this, I thought, well, it's not that hard to imagine how that would work. I could go find a plugin that would use TTP XYZ to provide create VXLAN tunnel, and it would know that that create VXLAN tunnel is a particular instance of create tunnel, and it would plug that in. And it could also do that over here on NVGRE and choose the right plugin and plug it in and map that up to create tunnel above that. As I thought about that, I didn't quite, so essentially if the guy up at the top said, give me a tunnel from A to B, it would know somehow to call create VXLAN tunnel. And if you said, give me a tunnel from C to D, it would know how to do that for NVGRE. And what I would like it to do is connect, if I say connect A to B or A to D, that it would also be so clever that it could stitch it together using these bridges in the way. But I didn't get so far as to say that I understand how that works. I can imagine that it's wanted, and it doesn't seem impossible to be able to figure it out, but exercise for the student at this point. But it's mostly like, I want to be able to think about what are the problems as we bash out this architecture. Let's think ahead towards different categories of problems.
So for those of you that are familiar with OpenDaylight, aside from this being the wrong color scheme, it should look reasonably familiar. And this is sort of, and I left the S off of the SAL because I was going to possibly rename it to an NDM-aware abstraction layer or something. But basically, I have two different things I sort of drew up. One of them, there are two different potential things you might want to do. Well, the first one is sort of the simplest thing you can imagine doing to support TTPs inside OpenDaylight. And so the gray area is the regions that have no idea what TTPs are and don't care. And the blue areas, the blue boxes are the parts that actually do kind of care. And so you can see sort of you have apps that don't care, and the OpenFlow southbound protocol and an abstraction layer, they don't care at all. They're just speaking OpenFlow 1.3. We already have hooks for OpenFlow 1.3, and those hooks for OpenFlow 1.3 work just fine. What does change is services that would like to be able to make better use of OpenFlow 1.3 can request a certain NDM, in this case it's a TTP, and that can go over from the service to sort of some registry maintained inside OpenDaylight that's going to basically be used and implement the algorithm that's going to try and negotiate TTPs at the bottom. And then that's going to go down to, so essentially this who populates the registry box, that's sort of the algorithm. I think this is a big open question, which is like, what happened? Magic happens here, then it sends them down to a registry of TTPs that it would like to negotiate. Those are then communicate back and forth with a negotiation module, which is going to sit on top of a southbound plugin. So we have southbound plugins for OpenFlow 1.0 and 1.3. 1.3 is the one which this would see the most sense for. And so it doesn't have any negotiation features in it right now, or the ones that it has are not. They're sort of later in the cycle than you would like them to be. So it can actually pass that information to the negotiation part of the OpenFlow 1.3 plugin, which we can add, and then actually negotiate the particular functionality at once. And once that's been negotiated, the negotiated TTP is passed back to this registry, which maintains not just a list of what I want, but a list of what actually exists in the network. And the services can query that and be able to find out, here's what's available, and as a consequence, here's what messages you're legally allowed to send back and forth. And this is sort of the minimum stuff that you would need. So you need to make a few services that are aware of the fact that TTPs are in fact a thing that exists. You need to have some kind of registry and an algorithm to populate that registry. And you need to have negotiation that we add to the southbound of OpenFlow 1.3. And if you got those things working, you could actually, without interfering with any of the current functionality, you could get a few services that could exploit this. And in fact, in the release, we have only one project that really uses OpenFlow 1.3 at the moment. And so this potentially has the advantage of letting other people use OpenFlow 1.3 because they'll actually be able to understand what they're doing. The second option really differs only in that you can expand the awareness of TTPs to include both the abstraction layer and the southbound protocol driver. And this has two real advantages. The first advantage is that the southbound protocol might be able to actually enforce the the TTP that it knows what is negotiated, and could throw exceptions or warnings when you sent messages up or down the stack that were going to cause problems. And if you can catch those exceptions and warnings in software on the controller, it's a lot better than having the switch send you bad val or whatever it is that it sends back to you and tells you nothing about why it is that it's wrong. And the second thing is that if you had an NDM-aware abstraction layer, it could actually provide assistance in providing services with the right APIs. So it could actually tell the services, here are the tables directly, rather than merely just like, and actually provide syntactic sugar to let people go right against subsets of the OpenFlow 1.3 protocol. And so this is where I think we want to get eventually, and I think you can get here from the first step. I guess we have 3.5 minutes left or something. I think that counter is right. So I'm going to walk quickly through the summary, and then basically the high point is that there's a huge variety of devices, but the assertion of TTPs in the forwarding abstractions working group is that these are bucketable by function. And so there's some level of abstraction sort of below OpenFlow 1.3, but above hardware, which is useful. And that we can build TTPs to imagine that area. And I have reasons to believe that that's actually true, which I can go into afterwards if you want. Applications want services and not just OpenFlow flow mods. And so using these services as sort of an intermediary between TTPs and applications in order to guide negotiation and really understand what you're trying to provide and provide northbound functionality out of TTPs and out of hardware, diverse hardware, is really sort of the whole goal of what we've been working on this time. And so hence the title of the talk, which is like, rich SALs to enable better functionality on diverse hardware. That's exactly what this is all about. And so that's really we could extend it to other southbounds, including I2RS, PCEP, et cetera. The last thing I want to leave with before I stop is how you can get involved. If you're in OpenDaylight and you want to participate, we're in the process of trying to figure out what we should be doing in order to get this code in there, whether it should be an extension of the OpenFlow plugin project, or whether it should be its own project and it's a project in its own right. And that discussion is going to hash itself out over the next probably couple of weeks. The Open Networking Foundation, if you're a member or your company is a member of that, you can attend the Forwarding Abstractions Working Group, which Curt chairs. And you can also get an early copy of the TTPs document. It does exist. And you can attend the workday after the Open Networking Summit if you want to. And then later on, the ONF should be publishing the TTPs document soon. And in the meantime, there's a link at the bottom of these slides, and the slides are available online like everything else. And I think you can just search for like Beckmann TTPs or Beckmann ND. Anyway, if you do a Google search for some relevant terms or copy this link, you can go find a slide deck which is available publicly, which describes some more details about TTPs than we went into here. And with that, I think both of us are happy to take questions in the 1 minute and 20 seconds that we have left that we have the room.
Typically, who does that validation, static validation, static and dynamic validation of the resource?
So that's a good question. The question is, suppose you're running low on resources and you want to do this create tunnel. I mean, how do you deal with that? Who's keeping track of resources? And as we said, because it's using existing OpenFlow messaging, there already is existing messaging, actually table features I think is part of it, that allows you to measure the size, how your table is doing against its limit. And so it's done within that, using those mechanisms to measure the available resources. There also are mechanisms that we didn't go into today where you can, at negotiation time, you can determine the size of the tables, which are a bit fuzzy for lots of reasons. But
in practice, actually determining whether a table is full or empty and how many quote-unquote rules a given flow mod is going to take when you put it into a table is one of these really frustrating things in practice in OpenFlow. And we don't do any better or any worse than current OpenFlow.
And we used up the time.
But until somebody kicks us out, we can probably take questions.
Yeah, kick us out if you need to kick us out, or if there's no more questions. Oh, there's a question.
Can you concern at all by kind of vendor-specific TTPs fragmenting and switch vendors only implementing, kind of creating their own versions and implementing them?
So the question was, do you see the ability for vendors to essentially subtype OpenFlow as taking away from the value that OpenFlow had as a common standard? If this was OpenFlow 1.0 and you could get things to work together, I would say no. Given that OpenFlow 1.3 doesn't work for switches and controllers at all, like if you get an OpenFlow 1.3 controller and an OpenFlow 1.3 switch together in a room and you hope that they do something, unless they're using one table, it's not going to work. So we already got there. We're already at the point where you have to have vendor knowledge of the actual switch hardware before you connect in order to do anything useful. And this at least makes it possible to make it open if companies choose to. And users can put pressure on them to do that.
Yeah, to answer that a different way, could somebody use TTPs to sort of do OpenFlow washing? Yes, they could do that. But I don't think that really delivers what the customers want. So I think there'll be market pressure to do it right. OK.
OK.
We're getting the hook.
So all right.
Thanks very much. And talk to us otherwise.